Okay, for this next proof by induction, I just want you to observe the following fact. So let's let um, A be less than B. Let's assume that these are both positive integers. And notice that 3 times A is certainly less than 3 times B. Okay, it's pretty simple. But is it the case that minus 3 times A is less than minus 3 times B? Well, no, in this case, because A is less than B and minus 3 is negative, this number, think of A as 10 and B as 100. Then we'll have minus 30 is less than minus 300. But that's not true. Minus 30 is bigger than minus 300. Okay, so when we have A is less than B, um, positive numbers maintain that, negative numbers don't. Okay, I apologize for that if it was really boring. So what I'd really like to prove for this next proof by induction is that, okay, so let h be some number that's greater than minus 1. It can be any real number. And I want to prove that 1 plus n times h is always less than or equal to 1 plus h to the n. And this is going to be for all n, I'll write it here, for all n greater than or equal to 0. Okay, so again, as with any proof by induction, the first thing you should do is write a predicate. So P of n will be just what we've written above, 1 plus n times h is less than or equal to 1 plus h to the n. And we want to prove that for all n greater than or equal to 0, P of n is true. Okay, so now the next step, as usual, is the base case. That's P of 0. So is it the case that 1 is less than or equal to 1 plus h to the 0, which equals 1? Yes. This right-hand side is 1, the left-hand side is 1. So the base case is taken care of. Okay. So the first thing we do is we assume that P of n is true. And what is P of n? It's that 1 plus n times h is less than or equal to 1 plus h to the n. So we can use this as a fact. And then we need to prove P of n plus 1, which is the statement that 1 plus n plus 1 times h is at most 1 plus h to the n plus 1. Now some of you might be saying, how can you assume that P of n is true? We need to prove P of n is true. No, we now need to prove that P of n plus 1 is true. We need to show that P of n implies P of n plus 1. So yes, the inductive hypothesis is that P of n is true, but now we need to prove P of n plus 1 is true using that fact. Okay? So we need to prove this inequality. I'm going to start by looking at 1 plus h to the n plus 1. This is equal to 1 plus h times 1 plus h to the n. Okay, now, this is good. I mean, I see a 1 plus h to the n here. My P of n involves 1 plus h to the n, so let's use our inductive hypothesis. This is going to be greater than or equal to 1 plus h times 1 plus n times h. So here's where I used the inductive hypothesis. I said that this term was greater than or equal to this term. And at the beginning of the module, I talked about how if a was less than b, then 3a was less than 3b, but not minus 3a versus minus 3b. So that's what's going on here. This 1 plus h term is positive because h is greater than minus 1. So since this is positive, again, 1 plus h is positive, it's okay. I mean, this term is going to be larger than this term. But it wouldn't be okay if 1 plus h were negative, but it is because we said h is greater than minus 1. If that little aside was confusing, just ignore it. So here we are. We've used the inductive hypothesis to transform this into that. So now, what can we look at? Well, we have 1 plus h times 1 plus nh. I'm going to expand that out, and I get 1 plus h plus n times h plus h squared. This equals 1 plus n plus 1 times h plus h squared. And this is certainly greater than or equal to 1 plus n plus 1 times h, because h squared is always positive. It's a square. So here we are. What have we shown? We've shown we started with 1 plus h to the n plus 1, and we showed that's greater than or equal to 1 plus n plus 1 times h. Well, that's exactly what p of n plus 1 asked us to prove. We wanted to prove that 1 plus h to the n plus 1 is greater than or equal to 1 plus n plus 1 times h, and here we ended up with 1 plus n plus 1 times h is less than or equal to 1 plus h to the n plus 1. So we've completed the inductive step, and that completes the proof.